Welcome back to BAS 120. We're on Chapter 7. We're going through the examples in the book. So the first one we talked about earlier, the legal analogy to hypothesis testing. So the key point here is hypothesis testing works much the same way. The null hypothesis, you assume the status quo. Basically, you assume that the person is not guilty. You collect sample data to test that hypothesis. And then you either reject the null hypothesis if you have enough evidence, i.e., find them guilty, or you accept the alternative hypothesis by rejecting the null. Very similar to the legal process where you assume that they're not guilty. You collect evidence, and if you have enough evidence, then you will decide that they're guilty. Now, notice you never prove a person innocent, or you never prove the null hypothesis. You just either accept or reject the null hypothesis. But it's helpful for many students to remember and keep in mind that it's very similar to the legal system. My null hypothesis is to assume the status quo, that nothing has changed. I collect sample data. If my data provides enough evidence for me to convince that my null hypothesis or my status quo is not true, then I can reject the null hypothesis. So let's go to example 7.2 where they do a CAD-soft analysis or an actual problem. So this is a one sample test of a hypothesis. We're going to assume something about the population or the population mean, and we're going to take one sample and test that hypothesis. Here I just gave you as a reminder some background on statistical terms. Alpha is our risk of rejecting, what level of confidence we want to have. Mu is our population mean. Sigma is our population standard deviation. Our population mu 0 is what we're assuming is a null hypothesis, is our population mean. Small n is our sample size. X bar is our sample mean. Small s is our sample standard deviation. SE is our standard error. Our test statistic, in this case, we'll be using a t statistic. Sometimes you'll be using a z. Z is often used when the standard deviation of the population is known. T statistic is used when the standard deviation of the population is not known, which is most frequently the case. So they use the z-test statistic if sigma is known, or you use the t statistic if sigma is not known. So the problem they gave us is they said the average response time at CAD-soft has been at least 25 minutes. So this is a technical firm. They get calls, and their response time is within 25 minutes to fix the problem. Now, CAD-soft has done some updates to their technical information to help with response time. So they think they've made this technical information has helped their clients or whoever to improve that response time. Now, CAD-soft, after the improvements, took a sample of 44 responses and wants to determine if the response time has improved significantly, and if it's, quite honestly, significantly less than 25 minutes. So, took a look at the raw data, which you can find in your in the raw database that comes in the Excel spreadsheets for CAD-soft. And here is the response times of all 44. And what I did up here is just simply took an average. Excuse me. And we used our average function. And since that's the average of our sample, that's our X bar. 21.909 on minutes. So the good news is it's a lot less than 25 minutes. So it looks like the response time has improved. What we don't know is we don't know if it's improved enough so that we're convinced that this didn't just happen by chance, or is this improvement so significant that we can say, you know, our new technical information has really made a difference. We don't know the population standard deviation. They didn't give us all the population raw data. So went ahead and used our function, there it is, to calculate small s, the sample standard deviation. So the sample standard deviation is 19.48, and you're going to see how we're going to use this information. So what we know so far is we know the average response time's 25 minutes. We put in technical improvements, and a sample of 44 customers tells us that the average response time is now down to 21.9 minutes with a sample standard deviation of about 19. So how are we going to use that information to try to decide whether this improvement is statistically significant? Well, if we remember our hypothesis testing steps, we have two approaches. We can look at the critical value approach or the p-value approach, and they're very similar. State the null hypothesis and the alternative hypothesis, decide a significance level, compute the value of the test statistic, and then we either determine the critical value or the p-value, and then we basically compare the test statistic to the critical value, and if it falls outside the rejection region, we'll reject the null hypothesis. If it falls within the non-rejection region, we will not reject, and we will conclude the null hypothesis has not been disproven. Remember, we never prove that the null hypothesis is true. We just prove that it cannot be rejected. So our goal in this is determine if improvement have improved response time significantly. Now notice this, we're only interested if they've significantly improved it less than 25 minutes. So we have a one-sided one-sided tail test that we want to do, and we're interested in the left tail because we're not interested in, if the response times made things worse, we're not interested in that. So our null hypothesis is that our response time is 25 minutes or greater, and our alternative hypothesis is it's less than 25 minutes. So again, note this is a one-sided left tail that we're interested in. So the next step is to decide a significance level, or our alpha, and I put 0.05. So that means if it's less than a 5% chance that these results happen just by chance, we're going to say that's enough for us to reject the null hypothesis. Step 3 is to compute our test statistics. So a couple things we need to know. We need to know what our hypothesized mean is. Well, they told us that they averaged 25 minutes. So we put in 25 minutes. Sigma's not known in this case. The population standard deviation is not known. So we substituted and we calculated what the sample standard deviation was. And in this case, we'll be using a t-test statistic because, again, in order to use the z statistic, we would have to have sigma be known. Our sample size, they tell us, is 45. Our sample mean, we calculated up there using the average function, 21.9. There's our alpha. Notice the type of test is a one tail to the left, so gave you a little picture. If it falls in here, we're going to reject. If it falls in this yellow region, we're going to accept the null hypothesis. Now, remember, the test statistic for a t is the numerator. We basically decide how far from mu is our sample data. So we took our x bar, our 21.9, that's the average response time we got in our sample, and compared that to what our hypothesized population mean was, which was 25 minutes. So we've reduced response times by 3.09 minutes. Now, the denominator of our equation, or our standard error, is our standard deviation divided by the square root of n. Because remember, as n goes up, we're going to shrink our deviation. So the denominator is our sample standard deviation divided by the square root of n, and n is our number of our sample size. So went ahead and in Excel, just put that in there, calculated it all. You can see the equation. and we got 2.937, and then our t-statistic is simply the numerator divided by the denominator, so we've got negative 1.05. So that basically means we're a little more than one standard deviation to the left, because it's a negative number, to the left of our mean. Now, we've calculated our test statistic. Now, step 4, we need to determine if that test statistic is far enough away from the mean for us to conclude that we can reject the null hypothesis. So a little diagram here for a left tail. If it's over in here, we'll reject. If it's over in here, we'll accept. Now we know our test statistic is negative 1.05, so that's somewhere over here, but we don't know exactly where. All right, so for a left tail, if our test statistic is less than this, we'll reject. Well, to find our critical value in Excel, we use our TINV, and we calculate it. There you can see it right there. And this is our hurdle point. So this is our hurdle. So the critical value is negative 1.06. Now, because this is not less than our critical value, we will not reject the null hypothesis. The other way, if we wanted to do it with a p-value, we would use the t-dist. And there you can see the formula there. You can go. I encourage you to go ahead and try this in your own Excel. So there's our t-dist, and what this is saying is there's a 14.9% probability that we would get 21.9 or less just by chance. Now, because the 14% is greater than our alpha, our 5%, remember we had said we only want 5% chance that this will happen by chance. We want it to be less than 5%. So because our p-value is 14.9, we will not reject the null hypothesis. And the same thing because our critical value is, because our t-statistic is not less than our critical value, which is what we need for a left-sided tail, left tail hypothesis, and because the t-statistic falls within this acceptance range, because remember, this point right here we just calculated is negative 1.68, and we're negative 1.05, so we're over here someplace well within the acceptance region. So we are not going to reject the null hypothesis, which is right here. We compare the values. There's our critical stat. There's our test stat. We do not reject. P-value 0.245. So there's almost a 15% probability of getting this sample by chance. This is not less than our alpha, or it's not, and therefore we will not reject the null hypothesis. So interpretive results, well, although our sample improved the response times from 25 minutes down to 21.9, this change was not significant enough for us to reject the null hypothesis. So we will conclude that the technical information did not statistically improve our response time. Now, what a business would probably do, since they've got some evidence that it improved, but not enough evidence to prove it in, is probably what they would do is next month take another sample, because remember, as the sample size increases, I'm going to again shrink that deviation, and I might, with a larger sample size, if my average of my sample continues to be 21.9, I might get to a point where I can prove it in statistically. So I have some evidence that there's improvements. I just don't have enough evidence. So again, just like a legal case, it would be like, well, we think this guy is guilty, but we don't have enough evidence yet. What they would do in the legal process is they would continue to dig to find more evidence. I think that's what you would do in this CADSoft example too. Just a note, below is the z-stat. So if we did z-test statistic, so if we had known what our sigma was, i.e. our standard deviation of the population, instead of using the t-stat up here, we would have used the z-stat. So that takes us through examples 7.2, 7.4, 7.5, 7.6. I thought I would lay out the whole thing so you had step by step how to do a one sample. This happens to be a left tail. Right tail would be very similar. Two tails would be very similar. There'll be an example of those. Hope this helps. Any questions, let me know.